Challenge like of you. you suck. All right, very nice. All right. Sometimes it's what you say, sometimes it's how you say it, and in the rare occasion it's actually both, like in a good metalcore song. Okay? All right. So we've been talking about sequences, right? This, comma, this, comma, this, comma, this, comma, this. And we haven't really been pausing like we're supposed to after the commas, but that's okay. We have a long way to go and a short time to get there. So what we're going to do today is, as I mentioned yesterday, replace the commas with plus signs, okay? So when you start adding up the terms in a sequence, you get what's called a series. A series is nothing more than the sums of the terms in a sequence that are generated by the same rule. Okay, and so we use the Greek letter sigma, which looks like the E, we've seen that before, to represent the sum. It's an operator, okay? So we'll write it like this, the sum from, and usually it's like from I equals 1 to 5 of some function of I, a sub I. Ours typically is going to be like this, though. Sigma from n equals 1 to infinity of some function of n. That's what ours is going to look like, more than likely. Or it might look like this, from n equals 0 to infinity of a sub n. Or it could look like even this, the sum from n equals 5 to infinity of a sub n. So the reason I write it several different ways is, first of all, n is still going to be our variable. Typically, we could switch to any variable that we want. We still typically use n for our rule of sequence, which now follows the sigma. But remember, for a sequence, we always start with n equals 1, always, right? The first term is always the first term, n equals 1. When you have a series, you can actually define n to start wherever you want, okay? At 1, at 0, at 5, wherever you want, okay? So long as you accomplish your goal. So the first term will always be associated with whatever the starting value is n is at the bottom, which could be 0. We never start with a negative number. So if it's not starting at positive 1, we're looking at whole numbers now. 0, 1, 2, 3, 4, 5, not negative numbers, okay? So what we're going to be exclusively, or primarily I should say, no, exclusively is good, concerned with is, do these sums converge or diverge, okay? When I add more and more and the sum gets larger and larger, are they going to get infinitely large, or do they converge towards a finite number? That's a much harder question to answer than, do the terms converge or diverge? All right? So we're going to be looking at a whole myriad of ways to determine whether these sums converge or diverge. We call these things infinite series, okay? Simply because we're going from some starting value up to infinity, which means we have infinitely many terms that we're adding. One of the ways, one of the early ways, one of the real intuitive ways to determine if a series converges or diverges is to look at, bless you, the sequence of partial sums and look to see if there's a limit to the sequence of partial sums. What do I mean by that? Well, if we let S sub n equal the sum of the first n terms, I can then figure out what is S sub 1. What is the sum of the first term? In other words, generate the first term, and that's it. And then I can look at S sub 2, generate the first 2 terms, add them together, compare it to the other one, add up the first 3 terms, add up the first 4 terms, all the way up to n. And then you look at the sequence. You're listing these partial sums in increasing order of the number of terms you're adding. If you can discern a pattern from there, you might be able to tell if a series is converging or diverging. So we're going to try that out. We're going to look at 2 different rules of sequences, 1 over n and 1 over n squared. So for the first one, 1 over n, we'll start with, sometimes you can get like extra time on your hands, and you can make your sigmas with some like cool little flares on them. But we're going to start at n equals 1 to infinity. And I can't start at 0 because 1 over n is undefined there. And we typically write the rule of sequence like that. All right, so there is my series. I've written it as a series now. How do we know it's a series and not a sequence? Yeah, the E, the capital epsilon, which actually is the Greek letter S. So let's go ahead and start listing the terms out. If I plug in the first n, I get 1 over 1. I'll just leave it like that. And now instead of a comma, I'll put plus, what's the next one? 1/2, and then plus 1/3, plus 1/4. Okay, so on and so forth, plus 1/5. And then you could do it this way, plus dot, dot, dot. You can either do it like that, which shows that it goes on. This is expanding out the entire series, by the way. And then you can even do what we did with the sequences. You can put another plus sign and then put the rule of sequence there and say plus dot 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 again. So that would be another equivalent way to list the series. The left side is the packaged up condensed version, and the right side is the spewed version. It's all expanded out, okay? But they're actually equivalent. So here's what we want to do. We want to compare S sub 1 to S sub 2 to S sub 3 to S sub 4 to, what did I say, the first, did I even say? No, let's just kind of go out and see if we can discern a pattern. So if we do that by hand, it can be somewhat of an arduous thing. What is the first partial sum, S sub 1? 1, right? You just add up the first term. Hey, here I am. It's 1, comma. The next term is a half, but we're not listing the next term. We're listing the partial sum of now the first two terms. So it's 1 plus a half. 3 halves. Okay, so there's the next number. And now, S sub 3 would be adding a third to a half. What's a third plus a half? Three halves, sorry. We have to add our previous sum. My bad, I asked the wrong question. You answered it right, Clancy. But it's the previous sum, but now I'm adding the third term. So 3 halves plus a third is what I meant to ask, which is 11/6. Okay, so you can see that this gets a little bit arduous. Dot, dot, dot. Now, just with these 3 terms in my sequence of partial sums, can you tell if it's getting bigger approaching a number or bigger approaching infinity? Hard to tell. So let's go to the calculators. Now, with math print, there was an upgrade to the sigma notation. Without math print, there was never a sigma notation. You had to take the sum of a sequence, which means you had to use list commands. If you go to second stat, you have list commands, and you go to math, you could take the sum of a sequence that you generated. Very, very not intuitive, okay? But now, with the new math print that everybody has, if you hit alpha window, which activates your F2, you see anything there that might be helpful for us? Number 2, summation. The math print actually has a sigma, and it's written in the format that we want. Oh, beautiful. Okay, bless you. So let's go ahead and establish a variable. We use n on our paper, but I'm just going to use x. It doesn't matter because it's 1 keystroke instead of 2. And we'll start at 1, and we'll put our rule of sequence in here, 1 over n. Or in this case, for me, it's 1 over x. 1 divided by x. So if you want the sum of the first term, the way you do that is you say, what is the sum from 1 to 1? Okay? So there it is, 1. Now, you can keep generating them like this. You can go back and change the 1 to a 2. And you get 3 halves. Right? So if you wanted to do this constantly, you could keep doing that. But you can also generate the next term by simply adding what the next term in the sequence would be, which for 1 over n, it's pretty easy for us. So write these numbers down as we go. 3 halves, I'm just going to say plus the next term, which would be a third, right? And that gives us that, which if we hit math, enter, gives us 11/6. Okay? You know what? I don't even want to hit math, enter anymore because it's easier to compare numbers with decimals, isn't it? Okay? So let's just write that as 1, 1.5 then. And then for 11/6, I'm going to put 1.833. And now for the next one, I'm just going to say plus, what am I adding now? The next term, which is a 4. So my sum is getting larger. It's an aggregate sum, 2.083. I'm writing these down. You can't see it, but I'm kind of listing right here the sequence of partial sums. All right, so if I add the next one, plus, what would be the next term? 1/5, pretty easy. 2.28, 2.283. I'll go to 3 decimals. Let's go out just a couple more here. Plus 1/6, and you get 2.45. And I think one more, and we'll kind of stop for analysis. 1/7, 2.592. All right, so I don't even know how many I have. 1, 2, 3, 4, 5, 6, 7. So I'm showing the sequence of the first 7 partial sums. Now we look for a pattern. Well, the pattern obviously is it's getting bigger. But the question is, does it appear to be getting bigger, approaching a finite number like we've seen with like asymptotes and graphs? Or does it appear to be getting bigger with no limiting value? It's hard to tell, isn't it? They are getting bigger, but they're staying in the twos, right? You might say that they're staying in the twos, so maybe they're approaching 3, right? Maybe they're approaching 3. Well, this is one way to do it. You can get real serious now with your calculator, because just like when we evaluated limits and we kind of like did our faithful duty of like choosing closer and closer values so we can see the limiting process, we see the limiting process, but you can quit messing around and kind of go, what's the sum from 1 to, I don't know, something outlandish like 20. It's 3.59. So now I know it's going to definitely get bigger than 2. Well, I don't know. You might want to put your goggles on. I'm going to go to 200, everybody. Safety goggles on. Oh, 5.87. I think one more. 20,000? I don't know. I didn't bring my apron to keep all the mess off that might happen, but this will take a while. Come on, calculator. Come on, you can do it. You're adding up first 20,000 terms. Okay. Right? Spring Fling's coming up, right, in 2 weeks. Now, here's the deal. But while it's calculating the sum of the first 20,000 terms, what would be your guess? Is it increasing, approaching a limiting value, or increasing indefinitely? It appears to be increasing indefinitely, because from your experience, by the time we go out from 20 to 200, if there were a limiting value, we would already see it increasing at a much decreasing rate. It would already be approaching something like 4.9, 4.99, 10.4, okay? If I had done 20,000 and the answer was like 4.9, or 5.9, sorry, 5.9, now I'd be a little bit more curious that maybe it's approaching 6, and I would do one more calculation, have a longer conversation while it does it, and then go from there. But I think there's enough evidence to decide that this series does what? It diverges. I believe that this series diverges to infinity, which means you can actually write it like this. N equals 1 to infinity of 1 over n equals infinity. You can actually say that. Okay? Because this is an operator. You're saying the sum is infinity. It's just another version of infinity. All right? Now, what if I started not at 1, but what if I made the sum smaller? Because infinity is a big number. What if I made the sum smaller by having fewer terms? Like, what if I started at 5 and didn't have the first 4 terms in there? That would make it smaller. You think that would make it small enough to converge? No. What if I started at 500 and took out the first 499 terms? That would make it significantly smaller, but not small enough. Yeah. It doesn't matter where you start. 1 over n is always going to diverge to infinity. Now, how is this similar to this? Yeah, it's actually very, very similar, right? We're adding up sums of terms in the top one, and on the bottom one, it's the same equation that's generating the growth. The integral, remember, is a sum from 1 to infinity, but now we're adding up areas. But remember, 1 over x was the guy that went to the x-axis lazy enough so that it diverged. It's kind of the same thing when you're looking at not areas but terms. It still goes so lazily that it diverges, okay? So 1 over n is going to be a very, very important one. We call this one the harmonic series. The harmonic series, 1 over n. It diverges. It goes to infinity, right? 1 plus a half plus a third plus a fourth. It gets infinitely large. And again, starting anywhere further down the line and taking out some terms, it's not going to matter. When you start adding them up, 1 over n is going to diverge. So now the question is, what happens if I do it with 1 over n squared, if I compare? from n equals 1 to infinity of 1 over n squared. Based upon now your experience with the improper integrals of the similar type, the integral from 1 to infinity of 1 over x squared dx did what? It converged, yeah. And not only did it converged to 1 over 2 minus 1. It converged to 1, the area did. Do you think this series will converge or diverge? You think it'll converge? All right. Let's go ahead and do the same thing again. Let's go ahead and list the sequence of partial sums. Again, this is one of the primitive ways to do this. You just you're gathering information, and we'll kind of do it the same way. The first term is 1, so I'm going to write that down. That's s of 1. If I add the next term when n is 2, that's 1 over 2 squared, which is plus a fourth. So that's 1.25. Now I'm going to add the next term, which is when n equals 3. That's going to be plus a ninth. So that's 1.361. And now I add the next term when x is 4. It's going to add a 16th, which is 1.423, ... Now, if you were to compare the partial sums, notice that everything that we're adding in this one is going to be a part of the sum of 1 over n, right? Here's 1. There it is over there. It's the first term. 1/4, we have a 1/4 there. So we got rid of the 1/2 and 1/3 terms. The next term that we had was 1/9. So then we got rid of the 1 over 5, 1 over 6, 1 over 7, 1 over 8 terms. So basically 1 over n squared has all the numbers that 1 over n had, but we took some away. And we're taking a lot away as we go further up. Do you think by making the sum smaller, by taking away a bunch of terms sprinkled throughout the sum, you think that's enough to make it small enough to converge? Yeah, your intuition tells you yes. Maybe your rational mind says, no, you're still adding infinitely many things, right? If you keep adding something over and over and over, it's going to get bigger and bigger and bigger. It's going to get infinitely large. So let's see. We can actually, again, get rid of some of the, fake ignorance about what's happening and just call this 1 over x. I don't want to give it away like too fast, so I'm going to call that 1 over x squared, but I don't want to go straight to 20,000. So let's just trim off some. Let's call it 20. It's 1.59. And remember, what we're doing now is something that back in the day before calculators, these calculations were super tedious. It took a long time to do this. Computers do this very, very quickly now. 1.59, 1.63. So we don't even really have to look at the sequence of consecutive sums. We can just look at trends for like orders of magnitudes. Let's look at 2,000. Oh, hey, whoa! Now by going a factor of 10, it got bigger, but now it's 1.63 to 1.64. That's an indication that maybe this one converges. Let's do one more, and be prepared to have kind of a lengthy conversation. Oh, yeah. All right, hit enter. I'm sorry. All right, so remember, tomorrow night, $10 gets you into the Alamo Draft House to watch dodgeball with a whole stadium full of your friends, right? And then you can order food, and then they'll bring it to you, and then you can say, I'll have another beer, and they're like, nice try. You didn't even have the first one. You're like, oh, right? Right, what's beer, right? Because y'all normally can't get in there because you have to be beer age. Ho, 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 ho. All right, so now 1.64, 1.644, 1.64. Okay, it's correct. It's the same to 3 decimal places. So if you had to guess, first of all, would this sum converge or diverge, you would now for sure say, hopefully, converge. If you had to guess what the sum is to 3 decimal places? 1.6. Ooh. I'm glad you didn't say 4,4 because you know the sum is actually bigger than that. Yeah, so in this case it makes sense to round up. I like that. That was nice. So this is, I'm going to put approximately now 1.645. Is that what you said? Dang, that's confidence. All right. I wish Miss Lincoln was as confident about filling the entire movie theater tomorrow night for dodgeball. Your help with that can help her confidence. Yeah, and you know what? You're right. So the second one does converge. And as you can imagine, this one is going to end up being a P-series. We don't call it a P-series integral, we just call it a P-series. And much like the P-series for integrals, it's going to be heavily dependent on the number 1, all right? And it actually works much the same way. So there you go. One method for discerning whether infinite series converge or diverge is by looking at a sequence of partial sums. Now, with the computers, with the calculators, we can actually then get approximations, if they do converge, to what those values are. But in general, it's two dramatically different questions. Does the series converge or diverge? Versus, if it does converge, what is the sum? Finding the actual sum is a much harder thing. It's not like an integral. We can just integrate it and find the answer, okay? All right, do the results surprise you? The fact that one of them gets infinitely large and the other one converges to something that's smaller than 2. If this was your first experience with it, maybe it would, right? Yeah, because they both seem to be kind of doing the same thing, but dramatically different results. But because of your experience with improper integrals, you now hopefully say, oh, yeah, okay, that makes perfect sense. Okay, so there's your introduction to series. We are now going to look at, some more, actually, and we're going to get into some specific tests. So what does it mean for a series to converge, diverge? Well, we already know. If you keep adding things over and over again, it gets closer and closer to a finite number. Here's a nice little way to look at a series. Let's say you have a coin, and if you had 1 penny, and every day you kept adding a half of the previous day's total over and over again. There's like a story about if you double something on a checkerboard, you're like a gazillionaire by the time you get to the 64th square. My question is, if you put down 1 penny and every day you kept adding more and more and more, but half of the previous day's total, will you also end up being a millionaire? Well, the first day I put down 1 cent, right? The second day I put down a half of a cent. The next day I put down a quarter of a cent. The next day I put down an eighth of a cent. The next day I put down a 16th of a cent. And the next day I put down, and these are hard to cut, these pennies this small, by the way. I put down a 32nd of a cent. If I keep doing that over and over again, notice I keep bisecting the region that's left, which theoretically, will it ever go away? No, it's like half the distance to the goal line. I'm kind of already running out of physical space to draw half of that. But in theory, you can keep doing half over and over. And if you keep adding all these together, you're getting closer and closer to what? How much money? There'll be a 2-cent error at the end of infinity. Yes?
It's kind of like the geometric version of that great paradox
of the Zeno's paradox. Yeah. And it is actually geometric. What we're doing here is 1 plus a half plus a fourth plus an eighth plus a 16th. And do you recognize that? That's what we just did, right? The only difference is we started with a half. Did we start with a half? Oh, we started with 1. It wasn't quite the same, was it? No, it wasn't quite the same. What we did here was this. We did 1 over 2 to the n. We did like an exponential function from n equals, and we started at 0 to infinity. That's essentially what we just did. And that does end up being a geometric series because, as we mentioned yesterday with the sequence, a geometric sequence is when you multiply or divide by something, you get the next number. In this case, we're multiplying by a half times a half times a half to get the next term in the sum. This is a geometric series, which is essentially an exponential function. And this one actually converges to 2. Pretty nice. All right. So the geometric series is one of the most important or hallmark series. So here's what it looks like. Is this the time I want to do that? Do I define it down below? Okay, I define it down below. So let me not give it away yet. But a geometric series is basically when you get the next term by multiplying or dividing by something. So given this series, the integral, or not the integral, sorry, the sum from 1 to infinity of 3 over 2 to the n, I wrote out some of the terms, 3 over 2, 3 over 4, 3 over 8, plus all the way out there. Do you think this one converges or diverges? Well, let's see. You can actually rewrite this. You could do what we do with integrals. A constant multiple of 3, you can actually bring it out front of the sigma. It's like the algebra of the sigma works just like it did for the algebra of the integral. So we're left with that. And of course, 1 to any power, if it's actually 1 and not approaching 1, is also 1. So I can say that's that. And this ends up being, then, because it's 1 to the n over 2 to the n, I can write that as 1/2 to the n. And this, based on my little story of the pennies, we know that equals what? We know that equals 2, just by a nice little visual. So that does converge to 2, and it ends up equaling 6. So this infinite sum, as you add up more and more and more terms, equals 6. Now, when we did sequences, and we took the limit, we never said that the sequence equaled the number, because we were listing them. Okay? But in this case, we're adding them up. Something plus something plus something equals, if it converges, you can write that there. It's 6. Okay? So this one does actually converge. And the reason why is if you look at the base, 1/2 to the n is kind of the same as 1/2 to the x, which would be what? Exponential growth or decay? It's exponential decay. And because exponential decay, our experience with the integrals, they definitely go to the x-axis fast enough to converge, much faster than p-series. Then if you have an exponential decay function, or what turns out to be a geometric series with a base that's less than 1, it should converge. Okay? It should converge. You want to verify that with the calculator? Again, this is something that is kind of new to me, because I wasn't able to do this until I got math print. So if I go to number 2, I could just type in x equals 1, 2, and of course we can't put infinity, but let's put 2,000. I don't want to wait too long. And then we'll type in our rule of sequence. You can still call it the rule of sequence. 1 over 2 to the x power. And then you hit enter. And it should be something close to 6. Okay, so remember, because it's exponential with the integral, we couldn't go out so far because it converged so quickly. Because this one's geometric, it gets so small so fast, I already overloaded it. So let's back off a factor of 10 and do 200. Okay. It's only 3 instead of 6. I'm glad we did this. I need to come back and correct myself. Why is it 3 instead of 6? Well, let's see why. What I did up here, I started with 1. I started with a penny. Right, I started down here with n equals 0. And this is a good thing to illustrate, because as I mentioned with sequences, we always start with n equals 1. But with series, you define where you start. So when n is 0, we started with a 1. The series that I just gave you started with n equals 1. So I never generated that first term. So this penny was gone, and I just started with a half. So if you just start with a half of a penny and keep adding, it adds up to what? Not 2, but 1. And so now I can amend my answer here. This is going to be 3 times 1, which is half of 6, which is 2. 3, 4, minus 1. 3. 3. Okay, good. I'm glad. I didn't really intend for it to work out that way, but it's a perfect illustration of, for a series, be very, very cognizant. I said very, very. Did y'all hear that? Like I'm watching a strawberry shortcake all over again. Be very, very sure of or aware of what the n value is where you start. Super duper important. And the calculator just put me in my place. Okay? We're not always going to have the luxury of checking on the calculator. All right. How's about this guy? 1 to infinity of 3 halves to the n. 3 halves, 9 fourths, 27 eighths. Do you think this one converges or diverges? Diverges. Very good. You're right. And we can see this on the calculator. I'm not going to. But if this were an exponential function, it would be f of x equals 3 halves to the x power, which would be exponential what? Growth. Yeah. And so just like if it were geometric growth, there's no way you can expect the sum to converge if your terms keep getting bigger and bigger, right? What's the only chance a series has if you want it to converge? You have to get to a point down the line where you keep adding less and less and less, namely approaching what number? 0. If you get to a point where you're adding 0 plus 0 plus 0 plus 0, then you have a shot at converging. We just saw, though, that up here, just because the terms go to 0 doesn't mean the sum converges. But it makes sense then that to have a shot at the sum converging, the terms at least need to go to 0, right? So that's why the sequence part that we did yesterday is so important. If the limit of the sequence is 1, then does that series have a chance to converge if eventually you're going to be going plus 1 plus 1 plus 1? No way, no how, okay? And that's another important test that we're going to be talking about soon called the Nth Term Test. So this one does diverge, and I'm not going to type it into the calculator, but you could do what we did, 20, 2,000, whatever, and you'll see that it gets really, really large. If you go to like 2,000, you'll overload it. So this one diverges. So much like exponential growth and decay, it kind of depends on whether the base is bigger than 1 or less than 1. What do you think would happen if it were 1? Let's do that. If n was actually 1 to the n. If it's greater than 1, we know it diverges. If it's less than 1, like a half or a fourth, pretty sure it converges. If it were 1, let's list out the terms. 1 plus 1 plus 1. That's going to what? Diverge. Yeah, okay, diverge. So here's your first test. This is called the geometric series test. We're going to learn several tests for determining if series converge or diverge without having the calculator and without having to list a sequence of partial sums. We're in here until 55. Okay. The geometric series test, or the GST as I call it. If you have a series of the form n going to infinity, or 1 going to infinity, or 2 going to infinity, the point being is that we don't have to start at 1. We could start at 0, or 1, or even 2, or 3, or 4. Of anything of the form a times r to the n. This looks a lot like exponential a times b to the x, doesn't it? So we have some a, which is just some constant, and then some base, which we're going to call r. We call it r for the ratio, okay? And then instead of x, we have n. Or it could be to the n minus 1 or n plus 1. That's not really that important, okay? What's important is that it has an exponential look to it. We call that geometric series. If, and this is cool too, in an exponential function, if we had f of x equals like negative 3 to the x power, is that a function? Can we have a negative base for exponential functions? No, because we're looking at all real numbers. And if you have a negative base for exponential function, you're going like negative 3, not just to the 1th to the 2nd, but negative 3 to like the 0.01 or the 1/2, which is the square root of negative 3. You cannot have a negative base. But we can actually have a negative base when we have geometric series because we're counting by positive values of n, integer values. Okay? So here's the cool thing. If the absolute value of your base, which we're calling the ratio, if its magnitude is bigger than 1 or equal to 1, we just saw that, like 3/2 or 1. Its magnitude is bigger than or equal to 1, the geometric series is going to diverge. It may diverge to infinity or negative infinity, depending on whether the ratio itself is positive or negative. But if the magnitude of your base is less than 1, and we can have a negative base, but if its magnitude is essentially exponential decay, then the series converges. And here's the cool part. Not only does it converge, just like with the P series, we can actually figure out the sum. It will always converge to a sub 1, which is your first term. And again, if you're starting at n equals 5, it'll be the first term when you plug in a 5. If you're starting at 0, it'll be the first term when you plug in a 0 over 1 minus r. So memorize that. This will show up. It's going to be one of the few series for which we can actually determine the sum without doing calculator partial sum stuff. Okay? Pretty nice. All right, very quickly, let's use the GST to determine whether the following serials converge or diverge. If they converge, find the sum. All right, so we've already done this one, but let's pretend like we haven't. First of all, is it geometric? Yes. Sometimes it needs a little rewriting. So there's n equals 1 to infinity, if you leave the 3 there, you can write 1 over 2 to the n as 1/2 to the n. And I kind of already showed you why that works. 1 to the n over 2 to the n. So this kind of fits the format of a times r to the n. So it works. So here's what you would have to say. The absolute value of r is equal to the absolute value of 1/2, which is equal to 1/2. That's less than 1, right? So it's actually more like an exponential decay function. So the series converges, and you might have to say sometimes by, or here's what you can say, it's a convergent geometric series. Let's just say the series converges by the geometric series test, and you would actually write that out on an exam. GST is not necessarily like the name brand. So the series converges by the GST to, and we can actually find the sum. We typically use the letter S for the sum, S sub 1 being the partial sum, S sub 2, whatever being a partial sum, but S being the actual sum, to the first term. Now what's the first term? Well, yeah, if you want to pull the 3 out front, it's up to you whether you want to contend with the 3 as being something times the whole sum or actually part of the rule. It's up to you. But if you plug in a 1, you get 1/2 to the first, which is 1/2, times 3 if you want to include it. That would be 3/2 as the first term. All over 1 minus, what is r? 1/2. So I've already gotten the r into consideration there. So that's going to be a 3/2 divided by 1/2, which is going to be times 2. And then you end up with the 2's dividing out and you get 3. Of course, if you wanted to pull the 3 out front, here's what that would look like. You can pull constant multiples out front, no problem. Now you just got 1/2 to the n. So it's still going to converge. And now the sum is 3 times. And now you use the formula. The first term now is just 1/2 over 1 minus 1/2. And you still end up with the same answer because you're multiplying by 3. So it's up to you whether or not you want to include the 3 as part of the rule or out front. That's pretty nifty. Okay? All right. This one, we already know this one what? Diverges. But if you had to say why, here's what you would say. The absolute value of r is the absolute value of 3/2, which is 3/2, which is greater than 1. Now, honestly, if you just said r equals 3/2, which is greater than 1, that would be sufficient as well. I just want you to get into the mindset that we can't have a negative value of r. And then so, the series does what? Diverges by the GST. You don't have to say to infinity, but because the base is positive, it does diverge to infinity. If it were a negative base, it would diverge to negative infinity. What else? Yeah, pretty cool. I wanted to say something, but now I forgot. Maybe it'll come up again. All right, how about this guy here? It's an infinite series. I can see that. It has a sigma, it has infinity. Is it geometric? Yeah, it's of the form. Here's your A. It's a constant multiple. Pull it out front if you want and call A1. This is a base raised to a power of n. So it has the exponential feel to it. That's the easiest way I can say to recognize it. Geometric series are exponential functions. All right, so does it converge or diverge? Converge. So here's what you would say. The absolute value of r is equal to the absolute value of a negative 1/2, which is positive 1/2, which is less than 1. So if this were a function of x again, for all real numbers, it would not exist. Okay? But because we're talking about positive integer values of n, we can have powers of negative numbers. So the series converges by the geometric series test, the GST, to S equals, now here again we want to be careful. I did not factor the 3 out, so I'm just going to take it as is. We're starting at what? 2. So go ahead and plug a 2 in. The first term would be 3 times, what's negative 1/2 squared? Positive 1/4. So there's your first term. It goes in the numerator. All over 1 minus what? Negative 1/2. That's super important, okay? When you're analyzing whether or not it converges, you take the absolute value of r, okay? You're looking at the magnitude. But in the formula, it's just 1 minus r. So if r is negative, it ends up being 1 plus r, which kind of makes sense, right? Kind of makes sense because if it becomes 1 plus r, it's actually making the denominator what? Bigger or smaller? It makes the denominator bigger, which makes the sum what? Smaller. And should you expect the sum to be smaller if every other term were negative? That's essentially what's happening, right? If you start listing this out, it's 3 times. When you plug in a 2, you get positive a fourth. When you plug in a 3, you get negative 1/8. When you plug in a 4, you get positive 1/16. This is an alternating series, right? There's an alternator in there, but it also affects the magnitude. So yeah, you would expect the sum to be smaller if you're subtracting every other term instead of adding it. So we end up with 3/4 times the reciprocal of 3/2, which is 2/3. The 2/4 divides out to give you that. The 3's divide out and you're left with half, which, yeah, is a smaller sum. Okay? So this is going to be known later on also as an alternating series. Some of these series that we talk about, they fall into multiple categories. Oh, I know what I wanted to mention now. Good. I'm glad my brain went back there. We call this a two-way test. It's a two-way test. What does that mean? You can actually determine if it converges or diverges by the same tests. Okay? Some tests are only one-way tests. We can only tell if they converge, or we can only tell if they diverge. And if it doesn't meet the criteria, we have to move on to another test to determine it. Okay? But for a geometric series, it's a two-way definitive test. If it fits this form and it looks exponential, then we're going to be able to tell whether it converges or diverges. If the base, which we call the ratio, is bigger than or equal to 1 in magnitude, it diverges. If it's less than 1, it converges. Okay, I'm going to stop right there. I think that's a good place to stop. And then we'll pick up tomorrow with the nth term test for divergence only. It's a one-way test, and it's going to end up being the very first thing that you always look for, never not first, when you're determining convergence or divergence of a series. It's the top of the flow.